Okay, in these three videos we're going to look at the process of nuclear fission as it applies particularly to nuclear reactors. So we'll also look at the reactor itself, and then we'll go on to the energy of the future, as they've been calling it for a long time now, and that's fusion, and how fusion occurs in stars and what that means for us. So let's start off here getting some background. If we're going to make electricity, you make electricity with a generator, and a generator has to spin in order to generate electricity. So you have to have some source of energy that will cause the generator to spin. This picture that I've chosen here is like a backup generator. You would put gasoline in this. There's a gasoline engine that then spins the generator. So gasoline is the source of energy to turn this engine, which turns the generator. So in the end, nuclear power, which is what we're talking about here, is about getting a source of energy to turn a generator. So keep that in mind as we go through here. Let's back up to the nuclear part itself. Nuclear fission means to split a nucleus. So you have a nucleus which is unstable. You usually do something to it and it splits. Here it shows a nucleus, protons and neutrons. It's hit with a particle. We don't know it yet, but that's going to be a neutron. And then it splits into two smaller pieces, and then we also get some other pieces. In this case, more neutrons are produced. Now, the fissioning of a nucleus produces huge amounts of energy. Here it shows 10 to the 13th joules per mole that we split. By comparison, if we use natural gas, which you may use to heat your house, it's what we use in Bunsen burners, you get only about 10 to the 6th joules per mole. So this is, it looks like there's only 7 different, right? But that's actually 10 to the 7th different. 10 to the 7th is 10 million times as much energy. So there's a lot of energy out of fission. All right, so the particular fission we do here is uranium. Uranium-235 is the unstable nucleus that's used in nuclear reactors. If we hit it with a what's called a slow neutron, then it will split apart into krypton, barium, and you get 3 more neutrons. So this is the nuclear equation for it. Take the uranium-235 nucleus, hit it with a slow neutron. We'll talk about that, what that means in a little bit. It splits into 2 pieces. It can be other pieces, but this is a fairly typical one. And you get 3 neutrons. Now that's the key to this. For every 1 neutron you put in, you get 3 out of this split. By the way, an exercise here nice exercise would be to stop and make sure this is balanced by adding up along the bottom and adding up along the top. I'm fairly sure I got it right. But this is an example of a nuclear fission reaction. Now here's the thing, because we get that, put that 1 in, split it, and we get 2 pieces and more neutrons, this shows only 2. You can get 2 or 3. This can become a chain reaction where the neutrons from one split go off and cause more splits, which cause more of these and more. So every time we have a split, we get double the number of neutrons. We can split double the number of atoms. Now notice that in this one, these are called the daughter atoms. The daughter atoms are different because we only get 2 neutrons. So this is different than the equation I showed you on the previous slide. Okay, now if you're going to get this to go and keep going, you have to have what's called the critical mass. If you have the critical mass, and it has to be calculated very carefully, then the neutrons will be trapped inside and they will cause fissions, and so each neutron will split more nucleuses and it will go very quickly and get a lot of energy. You can control that by how many neutrons there are and how much mass there is. If you have too little, the neutrons escape and the reaction stops. If you have too much mass, then it can explode, and that's what a nuclear or an atomic bomb does. Okay, so this is the end of part 1. In part 2, we will go on and look at the parts of a nuclear reactor.